Yeah, that's not part of this class.
I should have paid attention.
Yeah, that's always advisable.
Famous last words, right?
Always advisable. All right, so let's finish up the last one we were working on. On Tuesday, we had found the power series. So the stuff we're doing right now is a little complicated. We wanted to find a power series for this function g from the power series for the function f. And so the function f, we created the power series doing some substitution, and the interval of convergence for that power series for f was -1 to 1. And then we integrated the power series for f to get to the power series for g. And one of the things we talked about is that when you integrate or differentiate, the interval of convergence can change at the endpoints. The inside won't change, but it might change at the endpoints. So we ended up with this as our power series for g, but we didn't figure out the interval of convergence yet. So we have to test those two endpoints, the -1 and the 1. We have to test those. So all I did was plugged in -1 for x and 1 for x. So that's just right here. -1 and 1 for x. Right there. And -1 raised to this power, that power is always an even power. Right? 2k is always even, and if you add 2, it's still even. So that wipes out this numerator and turns it into just a 1. When we plug in the endpoint 1, we actually end up with the exact same series. Both of those series are alternating series. And in chapter 11, all we need to do is acknowledge that it's alternating. And the alternating series test intuitively, if it's alternating and the terms go to 0, it converges. So when we look at both of these, oh, it's alternating. And 1/2k plus 2 goes to 0. So both of those converge by the alternating series test. And so the interval of convergence, the I up there, is going to be -1 to 1, including the endpoints. So it started out excluding the endpoints, but we did an integration, and that gained convergence. And that's typically what we'll see. If the interval of convergence is going to modify, typically integration will add an endpoint or two, and typically derivatives will take away convergence at the endpoints. All right, so we have 2 more examples of this in this section, and then we'll go to 11.3. So here we've got a function. We want the power series for it, and we want to build that power series from a known power series. There's the known power series right there. So what we want to do is modify and tweak and try to create a power series for this. And the first thing that you probably see is this square root in here, and we would somehow have to create a square root over here. Any idea what we could multiply or do to this left side to invoke a square root?
Multiply by 2.
Close.
1/2.
Multiply by a half.
Then you can take it to the power.
Because we know a log rule, if you think about this 1/2 up here in the power, that could come down in front. So let's do this. Let's take that power series over there. If we multiply both sides by -1/2, we are going to have this. So I'm going to multiply by -1/2 on this side. All these parentheses. And forget about the expanded part. We're just looking at the summation part of it. So if we multiply both sides by -1/2, we have that. And then on the left, when we multiply by -1/2, if we combine the two constants here, we end up with a +1/2. And that +1/2 we're going to turn into an exponent on the inside. And we now have a power series for natural log of square root. So we're at this stage. And then we only have one thing left. We want this to be natural log square root of 1 minus x squared.
Substitute.
Substitute. Yeah, we're going to do that composition thing. So we're going to get, and that's going to be f of x, so I'll just call it f of x. So we're replacing x with x squared. So inside here, we replace this x with x squared. We're going to have x squared to the k, which is x to the 2k, and all that's divided by k. So all we do is a substitution at the end there, and now we have the power series for f. Now, anytime we have a power series, we want to think about the interval of convergence. That's kind of lockstep with the power series. We need to know what the domain, if you will, what the interval of convergence is. So, started out with this. What about multiplying a power series by a constant? Do we think multiplying a power series by a constant will change the interval of convergence?
No.
I hear some no's. Can anyone justify? It's true, it will not. Can anyone think of why it might not?
Well, it's either going to an actual value, in which case multiplying that value by a constant just makes another value, or it's going to infinity and or a non-single value.
So kind of like the convergence of a series is not affected by a multiplication by a constant. We can be a little more precise. What is the test we usually use to show whether a series converges or not, or a power series? We usually use the ratio test. And if you have an a sub k and you multiply it by a constant, when we take the limit for that ratio test, we are doing a sub k plus 1 over a sub k in absolute value. If this one is multiplied by a constant and that one is multiplied by the same constant, they cancel, right? They'll cancel out. So that's a good way to sort of think of it less conceptually and more mechanically, is that, oh, if we multiply a sub k by a half, then we're multiplying a sub k plus 1 by a half, half over half is 1. So it just disappears. So multiplying by a constant is not going to change the interval. Now we get down here to that substitution. Here we have to be a little more careful. There, when we look at the interval of convergence, we go with the original one was -1 less than or equal to x less than 1. But we now are going to replace the x with x squared. So let me just write that that's what we did down here. So we replace x with x squared. So now we have to replace this x with x squared. My strategy for doing this is to say the left side of this inequality is meaningless, right? That's always true, that x squared, doesn't matter what you plug in for x, that's always true. So why put it there? That's just extraneous. This is what matters, right? Because it's any x that you plug in here is bigger than -1. That's a negative number. This is always non-negative. So that's always true. And then we can take the square root of both sides, but we have to remember that the square root of x squared is absolute value of x. And so this leads us to this as our interval of convergence. We could write that as the open interval from -1 to 1. So that'll be the I. So we lost 1 point of convergence with that substitution. The last one on this, any questions on that before we go to the last one? Okay, so if we look at the last one here, this one is not so crazy. We've got our inverse tangent power series, already know it. And that interval of convergence is -1 to 1, including endpoints. All we're doing here is a substitution again. So the power series for this function, f, all we're doing is replacing the x with not just x squared, but 4x squared in this case. So we're going to come inside the summation. All we do is replace that x with 4x squared. So in the numerator, we'll have the quantity 4x squared raised to the 2k plus 1 divided by 2k plus 1. We could rewrite this and put the 2k plus 1 on the 4 as an exponent. We could multiply the 2 times that and separate it out. It's not necessary though. It's totally fine just to leave it like that. More importantly, we want to look at this interval of convergence. And so once again, we look at the original interval of convergence, which is that. If we replaced x with 4x squared there, we also want to replace x with 4x squared here. And then figure out the restriction on x. So these substitution ones are nice because we don't have to go do a ratio test and figure out anything new. All we have to do is this substitution and solve for x. We don't have to test endpoints. All we have to do is this. And so here, first I'm going to divide by the 4, so we have that. And then once again, we have one of these kind of funky inequalities where the left side is always true. The x's that satisfy this are the same x's that satisfy this. There's nothing, this adds no restriction on the x interval, right? The left side of that inequality is meaningless. You could put greater than or equal to negative 1,000, doesn't matter, right? It adds no new x's. It doesn't take away any x's from this one. It doesn't add or subtract x's. The solutions for this are the same as that, because x squared is always bigger than negative 1/4. So then we do the same thing. We can take the square root of both sides here. Just remember that the square root of x squared is absolute x. And so that gives us our interval. So our interval of convergence will be negative 1/2 to 1/2, including endpoints.
Is there a way where we're solving the x squared less than or equal to 1/4 that something we'd have to do to the x would switch it from less than or equal to just less than?
Say that once again.
So we have x squared less than or equal to 1/4.
Yep.
That's what we're solving.
Yep.
Is there some form of is there something that could be done to the x that would, to make it just x by itself, an absolute value of x, it would switch from less than or equal to just less than?
Not algebraically.
Okay.
Like if we had a series, I mean, we could lose convergence at that endpoint if we took a derivative, but just algebraically, there's no way that we're going to turn that less than or equal to into just a less than. Like if we had some series modification where we took a derivative,
So if we did all of this and then took the derivative of it and then it
then we
no
could
longer
lose.
converged, then
So if we looked at the derivative f prime here, then we could definitely lose convergence at one of those endpoints.
Okay.
Absolutely. But not just algebraically. There's no algebraic, process that would get rid of the equal part of it. Yeah.
It can change though, like in the last problem where you have one converges, one doesn't, and then since you're looking at one of them, it switches the other one.
Yeah, exactly. So up
There.
here, if this one's less than or equal to, and it vanished because that side became meaningless.
Yeah.
If this was less than or equal to, and this was just, that symbol is actually the greater than symbol, right?
Yeah.
So if this was greater than or equal to over here, and this was just greater than, that would disappear, and we'd end up with two brackets here. If this was there and not there, we would end up with brackets around
but since
that.
the left side's obsolete,
The left side is meaningless, so left side is just,
is there a possibility of the right side
Can
being
lose
meaningless?
convergence, but it depends on, I guess.
Yeah,
you
which
have, like,
one's meaningless and therefore could the right side be a meaningless
the right side is not going to be meaningless.
ever?
No, because there's always going to be a positive number there, so, well, I guess
Well,
it's
if you did negative x squared.
I guess
you did
if we
negative x
did,
squared, multiplied by -1.
The ones that we are going to see, we are never going to see the right side become
Don't worry about it
meaningless.
in this class, cool.
Yeah, don't worry about it in this class. Yeah, don't go there. All right, so then the last part of this chapter, this section, is just again the 6 power series that are based on the geometric series, and the next 6 that are based on the exponential. You want to play around with these. You want to get comfortable thinking about the sign. Let's go to the first ones first. So with the geometric series and doing things to it, integrating it, and I've told you what's happening up here. So here we integrate the geometric series to get that power series. Here we take we create the alternating geometric series with a substitution of -x. Here we integrate the alternating geometric series. This is just a shift from up here. We replace the x in here with x minus 1 and simplify it. And then we talked about how to get to this one. If you take the alternating geometric and you replace the x with x squared and then integrate, that'll give you the arctangent one. One observation, if you look at the arctan one, do you see it's all odd powers? Well, we had another one that was all odd powers on the next slide. If we come up here, all odd powers for sine, let's notice the difference. So sine has that expansion, and inverse tangent, what's the only difference?
You don't have the factorials.
So this has no factorials in the odds in the denominator, and this one has factorials. So the power series for arctan and the power series for sine are almost identical too. There's a lot of commonalities. But up here, remember sine is just the odd powers of e to the x, and you throw in a switch. Cosine is just the even powers, and you throw in a switch. And then the hyperbolic sine, same as the sine, except for the switch. You take away the switch. Similarly for cosine. And then there's that one, which we will get to today. The binomial series, which some of you, has anyone done the binomial series before? It used to be taught in college algebra. Like I learned it in high school. It used to be part of a college algebra class. The binomial series tells you how to raise a binomial, like a plus b or x plus y, to an integer power. So some of you might have heard of Pascal's triangle, which is a way to do the binomial theorem, the binomial series. We'll get to it today. Okay, so our last section before the next test. Test is a week from like today. So Taylor series, there's only one difference. Nothing new except this. That's it, right? We already done Taylor polynomials, and a Taylor series is just a Taylor polynomial that never ends. It's a really long Taylor polynomial. We just add dot, dot, dot. So be really careful. If you're asked for a polynomial, there should be no dot, dot, dot. If you're asked for a series, there should be a dot, dot, dot. Subtlety, but it's important to pay attention to that. Our series, lots of them are centered at the origin. The ones that are centered at the origin, we give a special name, the Maclaurin series. So if someone says find the Maclaurin series, then you automatically know that the center is 0. You don't have to ask the question, what is A? You know A is 0. So that's just a quick, easy way to indicate that the center is 0. So there's this thing here. It says for Taylor series to be useful, we need to know two things. We need to know where it converges, and we need to know where the Taylor series is actually equal to the function that you use to create it. And it turns out that these things are equal, that they're the same. So whenever we hear Taylor series, we think about taking derivatives and plugging in the center and building this. So you should be thinking of this as construction. You're constructing this Taylor series from a function. So the only way you can construct a Taylor series is if you can take the derivatives of that function. And then we find the interval of convergence. And in advanced calculus classes, you'll prove that wherever the Taylor series converges, it's actually converging to the function. It's equal to the function on those I values, those values from that interval. So we figure out where a series converges using the ratio test, possibly the root test, And wherever it converges, it's actually equal to the function that you use to create it. So the Taylor series and the function you use to create it are identical. And there is one and only one series. If you find a series for e to the x with that derivative process, or you find a Taylor series or a power series for e to the x some other way, they must be the same. There cannot be two distinct series that equal the same function. One and only one, which is great. Okay, so when we are asked to build a power series for a function, there are two ways. One is to use the Taylor construction process where you take the derivatives. The other is to use a known power series, which we've just done a bunch of, and manipulate it. Take a derivative, take an integral, do a substitution, whatever. So using a known power series to create a new one, or to construct. Typically, if the center is not 0, you've got to go through the Taylor construction process. Like if you look at these ones that we have up here, I think there's only one of them that's not centered at the origin. So if we're trying to find a Maclaurin series, a series centered at the origin, most of the time we can get to a Maclaurin series by manipulating one of these known power series that are already centered at the origin. Most of the time. In this class, if you see an a equals 0, you should think to yourself, oh, is there a known power series that I can massage to get to this new power series? You can always do the derivative process, but that's a pain in the neck. If you don't have to do it, you don't want to do it. But the time we do have to do it is if that series is centered somewhere other than the origin. Because we only have one known power series in our list that's centered at a non-zero number. Okay, so we've got to do the derivative process. Now, it's also asking us to write this in summation notation. And we need to do that in order to find the interval of convergence. To find I, you have to do the ratio test, or maybe the root test. But you need to have a sub k. The only way you get to a sub k is to write it in summation notation. We'll do a couple of those. On the exam, I'm not going to ask you to do that, because that you can get into a headspace where it's just hard. You know, it's like, oh, well, if I change this to a +1, change that to a -1, if I do a k + 1 or a 2k + 1, like it can get really heady. So I won't ask you to do that on the exam, but we'll do a couple of them in here that are on the easier side. So if I ask you on the exam, when I ask you on the exam for the IOC, it'll be, the series will be given to you in summation notation. Okay, so let's build the Taylor series here. So we do what we've always done. I'm going to go to y instead of f because there's less writing. And we're going to write it in a way that's easy to differentiate. And then we just start taking derivatives. And it's asking for, I think it said 4 non-zero terms. 4 non-zero terms. So not centered at the origin means that we can get to those 4 non-zero terms pretty quickly. So -2, we subtract 1, that becomes -3. Subtract 1 properly. Get that. That's the first derivative. That's the second derivative. And we should only need to go to the third derivative. So if we want 4 non-zero terms, we have our constant, and then the terms down here that will have an x, an x squared, and an x cubed.
Now, a lot of times that first term will be, if it is centered at 0, then you have to just disregard the first one and keep going. Or like,
Yeah,
for
exactly.
instance,
If
like
it's-
sine,
If it's,
sine, you have to skip the evens because your first 4 terms are going to be 3, 5, 7.
yeah, exactly. So if you have a function that's periodic and you get zeros, when you plug in the center, if you get zeros, you might have to go to 7 or 8 derivatives instead of 3 or 4. Yeah.
Plug in 0 here, you get all of
Yeah.
your
Yeah, here,
So-
well, here it's undefined at 0.
Exactly.
Here it's undefined everywhere at 0, so 0 is not even. So, question. If this is undefined at 0, what do you think the radius of convergence is?
2 or 1, sorry.
So this is undefined at 0. If we're going to center it at 1, we're 1 unit away from that vertical asymptote, so our hunch is that the radius of convergence is probably 1.
0.
So we'll see. Let's check. All right, so now we have to do the evaluation of our function and its derivatives at the center. So we're just going to come on through and evaluate. So same thing that we did for Taylor polynomials. Right? Nothing has changed. A Taylor series is a Taylor. It's just a long Taylor polynomial. Okay. Now we're ready to build. So our Taylor series, let's call it T of x. Because it's not going to have, like if we were just doing a Taylor polynomial of degree 3, we would write it as p sub 3, but we're not. We're writing it as an infinite series. So this is going to be 1 minus 2 times x minus 1.
Squared.
Not yet. Here comes the square.
Okay.
Here it comes. There it goes.
Okay.
Square. So square,
It's
the power
2
always
factorial.
matches with that. And then we have to also divide by the 2 factorial. And then we're going to get to our next constant, so minus 24. This is going to be x minus 1 raised to the 3rd power, and then we have to divide by 3 factorial. And to emphasize that, to indicate that it's a series, we just put the plus dot dot dot. So if we didn't have the plus dot dot dot, that would be p sub 3. We don't want p sub 3, we want the series. Okay, there we go. There's our Taylor series. Now, we have to come up with summation notation if we're going to do the interval of convergence. And again, we're not going to do, let's just do a couple of these. I am going to simplify this one just because sometimes when you simplify it, it becomes easier. Not always, but in this case it will. You know, so if you are trying to do an a sub k if you're trying to figure out what a sub k is, and you can't do it with the coefficients unsimplified, then simplify it. You got to try just both. It's, you know, sometimes both will work, sometimes one's easier than the other. It becomes pretty obvious here that our series is going to be, let's see, it's alternating. So we have a switch. I'm just going to put a k up there for a moment. Maybe it's a k plus 1. We'll fiddle. We'll fiddle with it as we need to, but we know it's going to have a power of a k or a k plus 1 for a switch. Okay, and then we have a coefficient in front of the power of x minus 1. And it certainly looks like the power on x minus 1 is just k. Let's all confirm that. And to me, it looks like the coefficient is k plus 1 in front. Right? If this exponent's 1, that's a 2. This exponent's 2, that's a 3. This exponent's 3, that's a 4. Let's see.
The first one, it's a 0 and a 1.
First one's a 0, exactly. We can think of this as 1 times x minus 1 to the 0. So let's see, does it match? When we plug in, first let's check the signs. Plug in 0, okay, positive. Plug in 1, negative. Plug in 2, positive. So the signs match. Plug in 0 here, we get a 1. And plug in 0 up there, this is a 1. Okay, so that's matching. The second term, we plug in a 1. We get the 2. We plug in a 1 up there. Yeah, so it's all matching. So there is our a sub k. Now with a power series, a sub k is the whole thing, including the switch for our power series. In chapter 10, you didn't include the switch. Chapter 11, you did. So now we have our a sub k. And this will lead us to the interval of convergence. So now we're going to take the limit as k goes to infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k. We're taking absolute value, so the switch does not matter. That thing is gone. No need the switch. So we're going to have k plus 1 that's going to be actually k plus 2, right? We're replacing the k with k plus 1. If we replace that k with k plus 1, we have k plus 1 plus 1, which is k plus 2. And replace this with k plus 1. Now that has an x in it, so we definitely need the absolute value. K plus 2 is always positive, so you don't have to put the absolute value around the k plus 2, but we definitely need it around the x's. So there's our a sub k plus 1 in absolute value. And then down below, we put a sub k. We've got that. What do the x's simplify to? X minus 1 up top, right? There's one extra x minus 1, and it's in the numerator. And that does not have a k in it, so it can come all the way out to the front. So then we're left with this. And what is the limit of that ratio? What do we think that is? Everyone agree? Limit's 1. Powers of k match, so we just look at the coefficients. Quotient of coefficients is 1. So when all is said and done, this overall limit is absolute x minus 1. Because this piece here goes to 1. 1 times absolute x minus 1. Now, conclusion of the ratio test. We want to know when that limit is less than 1. So we want to know, hey, what are the x's that make that less than 1? The x's that make that less than 1 are where the series converges. The x's that don't make it less than 1 are the x's where it diverges. So some x's will converge, some x's will diverge. This actually tells us instantly, as soon as the left-hand side of whatever you get from this limit, doesn't always work out like this, but we already have the absolute value expression isolated. There's no 2 in front, there's no coefficient in front. So that tells us that the radius of convergence is 1. As soon as you have the absolute value thing isolated, that number over there is your radius of convergence. You don't have to claim it right there. You could then do this next step. So we have that. We add 1 to all 3 sides, if we will. So we get that. So there are the bounds, 0 and 2, the boundary points for our interval of convergence. So our interval of convergence, we don't know what happens at the endpoints, but we know that. So the interval of convergence goes from 0 to 2, so the radius is 1. And so up here we could conclude it, or you could wait till down there. It doesn't matter. At some point you just have to tell us what the radius of convergence is. Half the length of the interval. So now we have to test. So we've got the 0 and the 2. We need to come over here and test. So we're going to test the endpoints. So x equals 0. So we're just going to the series and we're plugging in x equals 0 right there. Doesn't matter where the series starts. You don't even need to put an index if you don't want to. If you want to put it, doesn't matter, because doesn't matter. We have an infinite series. Doesn't matter where it starts. So -1 to the k, we have a k plus 1. And if we plug in 0 right there, we have -1 to the k. So this will be the series form, and -1 to the k times -1 to the k. -1 to the 2k, which is 1. Right. So this is -1 to the 2k. So that power is always even. If that power is always even, then this value is just 1. So we end up with that. Okay, and does that converge or does that diverge? That diverges by what?
Divergence test.
Divergence test. So the limit of k plus 1 is infinity, therefore diverge by divergence test. So we'll do the same thing with the other endpoints. So we're going to plug in x equals 2, and that's going to create the summation. Let's see, we've got the negative 1 to the k piece. We've got the k plus 1 piece. And if we come up here and we plug in a 2, 2 minus 1 is 1. 1 to the k is 1. 1 raised to any power is 1. So we end up with just that. So that times 1. What kind of series is this? Alternating. And with an alternating series, a sub k does not include the switch. So that's what we're going to consider a sub k. And does this converge or diverge? So it's going to diverge. You can say diverge by the alternating series test. You can say diverge by the divergence test. It doesn't matter. But we have the same conclusion as above. That limit is infinity, therefore it diverges. And you can say by dt or by AST. Doesn't matter. The terms are not going to 0. Must diverge. So, any questions on any of those steps? So therefore, the interval of convergence excludes both endpoints. Let's go to another one. So as soon as we see that the center is not the origin, we know we have to go through this derivative construction process. So we start with writing it, the function and its derivatives. If we want 4 non-zero terms, we need to go down to the third derivative, or further if some of them were 0. But none of these are going to be 0 because our center is pi over 4. So now we're just going to plug in the center into each of these and get our values. They're all looking about the same. A bunch of root 2 over 2's. Some negative ones down here. All right, so there are the values of the function and its derivatives. Now we can build our Taylor series. It's a function of x. So it will be root 2 over 2 plus root 2 over 2. And the next thing is x minus the center. This is going to be raised to the first power. So there's the tangent line. That's the tangent line. The next term, minus square root of 2 over 2, but we have to also throw in a factorial. We'll also have to throw in a factorial. So good question, though, that you just mentioned. Is this an alternating series?
Not quite.
Yeah, not an alternating series. For an alternating series, it has to be plus, minus, plus, minus, plus, minus. This one is plus, plus, minus, minus. And you can see from the pattern, when you take the derivative of this, it's going to go back up to here. It's plus, plus, minus, minus, plus, plus, minus. So it's not alternating, but it's got a bunch of negatives in it. All right, and then the next term is minus root 2 over 2, but we have to put a 3 factorial down there. And we're going to have an x minus pi over 4 cubed plus etc. So make sure if you're finding a Taylor series, you put the dot, dot, dot. And if we wanted to find the interval of convergence, we would have to come up with our a sub k, And we would have to then use the ratio test. I'm not going to do it again on this one. I'm not going to ask you to do that on the test, so, because it can get a little messy. All right, any questions on creating the Taylor series? You feel like you have that coefficient process down by now? It's not that hard to memorize. When you first look at that coefficient thing, it looks a little more complicated. You start to realize that there's a lot of symmetry in there. So we're taking the second derivative evaluated at the center to get that coefficient of the second order term. Now, when the series is a Maclaurin series, so in other words, a Taylor series centered at the origin, typically we're just doing that massaging of a known series. And so this is a series that we already constructed. It's on our list. This is the most important power series of them all. It is the one series. And if we want to get a Taylor series for e to the negative x, all we have to do is,
Multiply by e to the negative 1
so we're just going to take the x and replace it with negative x,
by 2.
right? It's as simple as that. So you can imagine the expanded form and replacing all these x's with negative x, but we'll just go straight to a sub k. It starts at 0. This x gets replaced with negative x. And if we simplify this, we are going to create an alternating series. We'll have a switch out in front, and then an x to the k divided by k factorial. The original interval of convergence is negative infinity is less than x is less than infinity. And when we replace that x with negative x, that nothing's going to change. We're going to multiply both sides by negative 1, but when we multiply both sides by negative 1, we have to flip the inequality symbol. So we end up with that, or you could write it in interval notation as that. So
It just flips that.
So it flips, as soon as we multiply by that minus 1 all the way through, each of those switch over, but we never write our intervals like that. So we want to rewrite it so that the symbols are in that order.
This is where it gets fun.
Yeah, no doubt. So now we've got this power series for Cauchy. All we want is the power series for Cauchy of 3x. So what do you think we do?
Multiply by 3.
So all we're going to do is replace the x in this series with 3x. So it's just a direct substitution. It's a composition. Composition is the math way to say it. So we're going to just replace the x with 3x. This will be our power series for f. And again, you can do some simplification type stuff in here. It's not necessary. I certainly am not going to ask you to do it. So if you distributed this 2k to the exponents, this would be 3 to the 2k. And what would 3 to the 2k simplify to?
9 to the k.
9 to the k. And then we would have x to the 2k. And then we would have 2k quantity factorial. So that would be probably the way you would be more likely to see it in an answer key. And a lot of times they'll pull the x's all the way off and might actually rewrite it so that it looks more polynomial in nature, so that the coefficients are kind of called out like that, and then multiplied by x to the 2k. And it looks a little bit more like a polynomial, but that's totally fine. So let's see, does the interval of convergence change? So the original interval of convergence was this, but we replace that x with a 3x, is that going to change anything? No. That's not going to change anything. If we divide infinity by 3, it's still infinity. So the interval of convergence, you can say it in a lot of ways. Sometimes you'll just see it like that. I should say equal to, actually. Element of, yeah. So I is an interval, though.
Yeah.
So I shouldn't say element, so I should say that. You can see it like that. You could write it in interval notation as negative infinity to infinity. Or you could write it like that. Doesn't matter. All those things are same. All right. You all try one. So write out the Taylor series for natural log of x with a center of e. Find the Taylor series. Maybe I should say build the Taylor series. Build the Taylor series. I don't know that I've ever seen someone come to class with a roll of paper towels. You brought that?
No.
You didn't bring that?
No, that's good.
It was already here?
Yeah.
Really?
Figures.
Oh, they're mine now. I'll take them. They were just sitting on this table?
Yeah.
You'll get
us credit for that.
Yeah. I'll give you plus epsilon. That's a lot, right? That's so funny that did someone already have like an end of semester party? It wasn't a math class.
Tears.
Oh, there was a
Wasn't
test.
test, yeah.
The tables are set up for exams, so maybe that is. Yeah. Someone's collecting.
How kind of the professor.
Okay.
Hey, I see that you're crying. Could you please down? Here's some tissues.
Here, I'll give you a paper towel.
Yeah, go for it.
Not Charmin.
Try to blot them out, otherwise you'll hurt yourself.
Bound to you. Quicker picker upper.
Wipe out all these tears.
Maybe they still coming.
That's possible.
Yeah, my tears.
Your brains.
We just need to set up the equation for the Taylor series, or do we need to evaluate?
Yeah, just do the setup. You don't have to find the I or anything, so yeah, we'll keep it simple, quote unquote.
It's relative.
It's all relative. Hopefully, you can hammer through your derivatives really fast. Hopefully, taking derivatives is trivial by now. So now we're going to plug in our center. Natural log of e is 1. And then we have 1 over e, or e to the negative 1, 1/eth. So any question up to that point in time?
Yeah, but you didn't realize.
Then our Taylor series. So much of this power series stuff is just bookkeeping. It's just keeping things in order. If you come up with a process where you just keep things organized, it's pretty straightforward. So it's that constant plus the next constant times x minus the center. So there's the tangent line. And then the next constant, minus 1 over e squared, but this one has that modification with the factorial. And then x minus e squared. And then the next constant, 2 divided by e cubed modified with the 3 factorial, x minus e cubed plus dot dot dot. Feeling pretty reasonable? All right, the last one before we get to the binomial series. The binomial series is going to be very fascinating. Okay, so 10 to the x. Same idea. We've got this exponential function. It's got a base of 10. We'll start by taking 3 derivatives. When we differentiate an exponential that has a base other than e, that's where we have to throw in the extra factor of natural log of 10, or natural log of that base. If the base was e, natural log of e is 1, so it also is true for that one. So there is the function, first 3 derivatives. None of them are going to be 0. That's great. Plug in our center. So y of 2 is going to be 100. Y prime of 2 will be 100 log 10. Y double prime of 2 will be 100 log 10 squared. If you want, you could put the 2 on the ln like they were doing in the prior chapter. Or you can put it on the outside the more traditional way. Anything up to that point cause you grief? All right, now we're ready to rumble. Our infinite series is the first constant plus the second constant multiplied by x minus the center. And then the next constant, 100 natural log of 10 quantity squared divided by 2 factorial times x minus 2 squared. And then the last constant, 100 natural log of 10 cubed divided by 3 factorial x minus 2 cubed plus dot dot dot. Yeah, not too bad. Seems easy enough. Feels like it's got a nice discernible pattern. How about writing this one in summation notation? This one looks a little less ominous. Let's see, could we write this one in summation notation? Well, they all have 100 in them. You could factor it out if you wanted, but let's just leave it in. And then they all have, power of ln. So ln of 10 raised to the k power. So when k is 0, that's just a 1. When k is 1, that's going to put there. And so that's x minus 2 to the k divided by k factorial. So this one's not too bad. Here's k factorial. So if we wanted to find the interval of convergence, we would then apply the ratio test there and test the endpoints. All right. So let's talk about binomial coefficients. Has anyone had stats in here? No one has had stats. Sometimes in algebra classes they do a little bit of stats. So binomial coefficients are those coefficients that are written, they look kind of like a fraction, but it's not a fraction. This is pronounced P choose K. So when you take an elementary stats course, you pronounce that P choose K, and usually, until you get crazy, until you get to Calc 2, these are positive integers. And P is going to be bigger than K. So the idea that a lot of times is used to convey the idea of a binomial coefficient. You do the ball thing. You have a bag with a bunch of balls in it, and it's like, and some are red, some are blue, some are yellow. You know, what's the probability of picking out one red ball out of, the bag of balls? So P choose K. So this is going to be P choose K. The choose is the number of ways you can pick the one ball out of the bag. And the coefficient's going to lead to the probability of that event happening. So the coefficient is the P choose K part. In your mind, you're saying how many ways, let's just suppose we have a bag of 3 balls. How many ways can you pick 2 balls out of the bag? You can pick ball 1 and 2, you can pick ball 1 and 3, you can pick ball 2 and 3. So there's 3 ways. So that coefficient's going to give you that number, the number of permutations. Now the formal definition of P choose K is this right here. So this expression is the formal this is how you'll learn it in a stats class. Everything is a positive integer, so all of these factors make sense when you're dealing with positive integers. 2 factorial, 3 factorial, whatever. So traditionally, if we wanted to figure out what, let's say, 7 choose 2 is, so the idea in your mind that is then, okay, I've got 7 balls in a bag and I want to pick 2 out at random. How many ways can that happen? That's what 7 choose 2 is going to give you. All of your calculators have this option on them. If you go to the stats menu, 7 choose 2, will be an option. So here's how we would traditionally do it. We would do 7 factorial divided by 2 factorial. So it's the upper number, the P factorial, the lower number, the K factorial, and then you multiply by the difference. So then it's going to be, I don't need a parenthesis there. So then you take the difference. 7 minus 2 is 5. So that's how we fill in the denominator with that extra factor. Okay, so right now it feels like, oh, we can only do this for positive integers. But then there's this clever little observation. In the numerator, isn't the numerator 7 times 6 times 5 factorial? Well, you can cancel out that 5 factorial with the denominator, and you can actually write your binomial coefficient in a way that there's no factorial in the numerator. There's still a factorial in the denominator, but there's no factorial in the numerator. And so what this has done up here, I would never write this formula down the way it is, because that's super complicated looking. But the idea is this, that that formula right there is representing, so let's think about what we have in the denominator, k factorial, that's 2 factorial, right there. And in the numerator, you start with your p, that's the upper number, and then you do repeated subtraction by 1. This many times. So maybe I shouldn't say repeated subtraction by 1 this many times. You should have 2 factors in the numerator when you're done. So we start with p, and then we subtract 1, and we're going to keep subtracting 1 repeatedly until we have that number of factors. Let's just do one more quickly, and then we'll take our break. So if we wanted 7 choose 4, we would write this as 7 factorial over 4 factorial, and then the difference factorial. And then the 3 factorial is going to cancel with the numerator and leave us with 7 times 6 times 5 times 4. And we've got that. Right, because the 3 factorial would wipe out the end here. And so again, notice that this number right here, the k, tells us how many we need. So we start with 7 and we do repeated subtraction by 1 until we have k factors. And that's what this is saying, but is very hard to convey. So up here, this numerator is k factors. So they're telling us up here in this generalization to keep subtracting 1 until you have k factors. So we'll take a break there, and then we'll talk about what the implications are with this modified definition from that definition. We'll talk about that. All right, 10 minutes. Okay. So the binomial theorem, the binomial series, blah, blah, blah. The idea behind it is that what it allows us to do is expand a binomial raised to an integer power really fast. And I'm sure some of you have seen Pascal's triangle before. You start with a 1, you start with these right there, and then you just add the 2 numbers that are directly above it. 1 plus 1 is the 2. The 1s come down the column, and then the 3 is the sum of 1 and 2. The 3 is the sum of 1 and 2. 4 is the sum of 1 and 3. 3 plus 3 is 6, etc. And the binomial coefficients can be found from Pascal's triangle, right there. So if you get good at Pascal's triangle, you can expand these binomials really fast. Okay? And that's all fun and interesting from an algebra point of view. If you do it with the definition, the factorial up here, this coefficient is 5 choose 0, this one's 5 choose 1, and you get the same numbers, okay? So, like we did over there, if we did 8 choose 3, first we write 8 factorial and then 3 factorial, and if we can't, and then 5 factorial is the difference, 8 minus 3 is 5. And then the 5 factorials cancel, and once again we get to this place where whatever this k value is, that tells you how many factors you have up top. So, like I mentioned before the break, in the numerator you have k factors by doing repeated subtraction by 1 and no factorial. And here's where the math people got all excited back in the day, like, oh. That means if we generalize this, we can start using weird p-values that are not positive integers that are bigger than the thing. So now, all of a sudden, we can't visualize like a context anymore. It really is easy to imagine, oh, we're going to pick 3 balls out of a bag of, whatever. Pick 2 balls out of a bag of 8. How many ways can you do it? Like that you can visualize. This stuff you can no longer visualize. It's kind of like the imaginary unit. It mathematically has a nice structure to it, and it's easy to do mathematically, but you can't really visualize it very well. Like, what does it mean that the square root of -1 is I? Like, that's a definition that we build off of. That's not something that we have a nice practical visualization for. There is some visualizations for it that involve rotations that you'll get to later, but it's not as intuitive as like an algebra thing that you could visualize. So here, we're just going to apply this new way of doing the binomial coefficient. we're going to say, oh, okay, just start with P. There's P. Yeah, P, right? It's P choose K. Yeah, P. Start with P, and then do repeated subtraction by 1 until you get 3 factors. 1, 2, 3. Boom. That's what that's equal to. Doesn't have like a physical thing that you can interpret it by, but you can mathematically define the binomial coefficients now for p-values that are any real number. Right? If you're just going to do repeated subtraction by 1, we can do that with any real number. So now we get that coefficient is equal to negative 5/16. Okay, so let's do some examples then. Let's go here. So the binomial series, so let me just point out one thing back here. As soon as that p-value is not a positive integer, this is going to go on forever and ever. When that's a positive integer, you end up finishing and you get a finite expansion. As soon as that p-value is not a positive integer, this is an infinite series. As soon as you make that. So, again, these are really hard to write out. It's much easier. Here's how I would write out. If you were so inclined to write out an expansion, this, I would say, is the best way. P choose 0 plus P choose 1 times x. So instead of writing out those coefficients in a modified, expanded way, this is what you should be thinking of when you're talking about the binomial series. So just think of the coefficients in that binomial coefficient way. Like trying to write all this out and make sense of it is, that's like voodoo. That looks very familiar. Doesn't it look like the geometric series with tweaked coefficients? Right? 1 plus x squared plus x cubed plus x to the 4th. Right? These binomial coefficients are just replacing the standard coefficients for a geometric series. So the binomial series should look like a geometric series with these tweaked coefficients. But that's the way to visualize it. Sum of powers of x with a tweaky coefficient. Now, the binomial series has 3 different intervals of convergence depending on what p is. So these are the 3 intervals of convergence. They all have the same boundary points, -1 to 1, but based on what p is, that dictates whether you include or exclude those endpoints. You cannot figure out whether there is convergence at those endpoints yet. So this will always be given to you in this class. There's no way to figure out with the ratio test because that's your a sub k. Like trying to figure out using the ratio test whether you include or exclude the endpoints is not easy. It's very, very difficult. So at this stage, binomial series, you know it's going to be -1 to 1, and I will give you this piece to tell you whether you include the endpoints or don't, depending on the p-value. So if p is positive, you include both endpoints. If p is between -1 and 0, you exclude the left endpoint, and if p is less than or equal to -1, you exclude both. But that'll be given to you.
And you can never have a p of 0? Because of...
Yeah, p cannot. Yeah, p is never going to be 0. So
Gotcha.
yeah, p is not going to be 0 because this numerator then is always going to be 0 then. So it's
Makes sense.
so you don't really have a series anymore.
It just doesn't. Gotcha.
Degenerate series. So, I wrote it right there. Yeah, duh. So that's the way you should be sort of thinking about the binomial expansion. It's just a modified geometric series. So let's check it out. And the whole point of writing things as power series is that they're easier to deal with. You can code them into Oh, we haven't talked about this. Have we? No, we have not. So you are using power series every single day. Whenever you touch your calculator, whenever you do any calculation, that's done with a power series. If you want to type into your calculator e to the 2, it looks at the power series for e to the x. It replaces the x with the 2 because the power series for e to the x is a polynomial, and it just has to go far enough out that the accuracy fits your display, right? There's no, if you're doing sine of something like pi over 5, there's no unit circle in the calculator with a little ball moving around the unit circle. It looks at the power series for sine or cosine, whatever angle you're going to plug in, whatever trig function you're going to plug in. It looks at the power series. It looks at the number you're plugging in, does a quick calculation on how many terms it needs to give you so that your display is accurate. So all of our computational devices are using, I mean, technically they're using Taylor polynomials because they're chopping off the tail. But the idea is, oh my gosh, my wife is here. Hi, honey. How could you not? So the idea is that you are, as you type that into your calculator, the calculator's doing a quick little calculation and says, okay, we need 12 terms. It can add and multiply really fast, right? You can program addition, multiplication, subtraction, division really easily. So, right, no unit circle in your calculator. Right, so power series are the backbone of all mathematical computations when it comes to using functions. All right, so if we type that into our calculator, same thing. It needs the power series for this binomial. So let's find it. So this binomial is, what's the p-value for this binomial? So p-value is the power, so let's just rewrite this. So that we have that. So the p-value is always the power that we see on the binomial. So that is p equals 1/2. And now we want to rewrite this thing, this function. And I'll always sort of write this out first just to try to reinforce that the binomial series is just a modified geometric series. It looks a lot like a geometric series, except for the coefficients. There we go. A geometric series has predictable coefficients, right? Each one is a multiple of the prior one. There's a common multiplier. That's not the case with these coefficients, so it's just geometric-ish. All right, so p choose 0 is always 1. Oh, let me put the half in first. Well, so we're going to have 1/2 choose 0, and then 1/2 choose 1, and then 1/2 choose 2, and then 1/2 choose 3. We'll just go that far out, unless we want to go further. So there we go. So 1/2 choose 0 is always 1. So p choose 0 is always 1. This never changes. That's always 1, and this one is always going to be p. Okay. So this one, like if you think about the ball thing, if p was 5, 5 choose 1 is saying how many ways can you pick one ball out of a bag of 5? Oh, 5 ways. You pick any of the 5 balls that are in there. How many ways could you pick 0 balls out? 1. You don't pick any balls out. So that will always be 1, that will always be p, so it's pretty fast to write down the first 2 terms every single time. It's always going to be 1 plus whatever p is multiplied by x. All right, now we have to do some computation. So let's come off to the side and do a little computation. So 1/2 choose 2 So in the denominator, there's going to be a 2 factorial. And in the numerator, you start with p, and then you subtract 1 repeatedly until you get to k factors. So since k is 2, we only need 2 factors, so we only have to do 1 subtraction of 1. So that's it. We're done there. So in the numerator, we have -1/4. Denominator, we have 2, so this will turn into -1/8. So that is our next coefficient down here, -1/8 x squared. All right. Now we go to a half choose 3. So 1/2 choose 3. So same thing, we're going to start in the numerator with 1/2. We are going to do repeated subtraction by 1 until we get to 3 factors. So we started at 1/2. First subtraction takes us to -1/2. Subtract 1 again, we get -3/2. Done. We have 3 factors now. 1, 2, 3 factors. Now we can simplify this, so this is going to be +3/8 divided by 3 factorial, which is 6. So we're going to have 3/8 divided by 6 means multiply by the reciprocal, 1, 3 cancels, and we're going to get 1/16. So that is this coefficient, 1/16, x cubed plus, etc. The next coefficient will not be 1/32. It will not be. There is no pattern. The pattern is this. There's no like algebraic pattern multiplied by something. The pattern is that binomial coefficient. There's not going to be some other numerical pattern that you can create. It's that. These coefficients. So there it is. So there's no way for us to write this in summation notation. We just leave it like that. So you'll be asked for the first 4 non-zero terms. It's a series. Make sure you put the dots. There it is. So that is the infinite series for the square root of 1 plus x. So next, it says approximate root of 1.06. So my first question is, what is x going to be up here?
0.06.
Correct. So x, we're going to plug in 0.06 for x, because this is 1 plus x. So x is the difference from 1. So 0.06. So the square root of 1.06 will be approximately equal to 1 plus 1/2 times 0.06 minus 1/8 times 0.06 squared plus 1/16 times 0.06 cubed.
Now, the further you go, is that going to give you a more accurate?
100%.
Okay.
Yep. So the further we go out in that series, the better the approximation is going to be. And let's just go to Desmos for a second. So, and one thing in Desmos, you know you can do summations in Desmos, right? I can't remember if we've done that or not. My mind, I didn't sleep enough last night. Now we can't write a series, we don't know a sub k here, so we just have to type this out. We can't do a shortcut with an a sub k, but if we had an a sub k, we could certainly do it. Oh my gosh, what happened? That's supposed to be a plus. And this gives us our approximation that should be pretty good. So let's do the square root of 1.06. I guess I could have done that with SQRT. So that is pretty good. That's, I don't have my glasses on. How many decimal places does it match?
7.
Matches a lot for that simple little polynomial.
6.
So that's the idea. So that's what your calculator is going to do. You know, if your calculator has a display that can handle 10 decimal places, it'll make it out, it'll go far enough out so that you have 10 decimal point accuracy. Which is why that error calculation we've sort of alluded to a lot in the last few weeks, is why that's so important. Right, you want that error to be less than 0.10 zeros and a 1. All right, let's try another one. So now we have a p-value of -3. All right, so now we're going to go with a negative number. All right, so that's just a binomial raised to the -3 power. P is -3. So f of x is going to be equal to -3 choose 0 plus -3 choose 1 times x plus -3 choose 2 times x squared plus -3 choose 3 times x cubed plus etc. All right. When we rewrite this, it's super fast for the first two terms. -3 choose 0. Choosing 0 can only be done one way. Don't do anything. So the first two terms are always instantaneous. Always 1 and always p. So then we have to come over here, do a little work on the side. -3 choose 2. In the bottom we have a 2 factorial. In the top we start with -3. And then we subtract 1 repeatedly until we get to 2 factors, so just one time. So this is going to be 6. So there is our coefficient of the square term, 6x squared. And then we go to the next one, -3 choose 3. Whoops, same idea. -3 choose 3. In the numerator, we start with -3, we subtract 1 twice to get to 3 factors, and in the bottom we have 3 factorial. This is going to end up being negative. 3 cancels, 2 goes into 4 twice, so we end up with -10. That will go there. So f of x is exactly equal to that on the interval -1 to 1. Now, if we wanted the exact interval of convergence, again, I said that that would be given to you. So if we wanted the exact interval of convergence, we're going to see that we don't include the endpoints. If we come back up here, less than or equal to -1, we don't include the endpoints, but that has to be given to you. All right, so any questions on that computation or building that series? Pretty straightforward. All right, so that now let's say that we want this approximation. So we are going to say that, let's go with the approximation. So 1 over 1.331, it's equal to 1 over 1.1 cubed. And that's going to be approximately equal to, let's see, 1 plus x. That's in the denominator, right? So what is x in this case? 0.1. So it's going to be approximately equal to 1 minus 3 times 0.1 plus 6 times 0.1 squared minus 10 times 0.1 cubed. Let's see, is there a shortcut? not. 1 minus 3/10 plus 6 over 100 minus
10 over 1,000.
10 over 1,000. Whoops, that one. Whoops, was it a
Well, 10
Wasn't
over
a one.
100, 10 over 1,000.
10 over 1,000?
Or just-
Or 1 over 100.
It's not bad.
There we go. And then this is 1 divided by 1.331. There we go. There is our approximation.
Much worse approximation. It only gets 2.
Right?
Did the last one, which got 1 second.
Yeah, we were way out there in the last one. Yeah, so it'll just keep getting better. Question, Robert?
Yeah, can you explain that black portion right there?
Right here?
Yeah, well, yeah, to the right of it, approximate.
So
You just plug into,
we're looking at, we have to identify what x is first. So x is added to 1. So when we look at this denominator is 1,
okay.
1.1, so it's 1 plus 0.1 is the denominator. So the x value is going to be 0.1. And so for the approximation, where we're going to go out to this third order approximation, we're going to replace all the x's with that 0.1.
Okay.
Is this one an alternating series? This one is an alternating series because every time you can see when we subtract 1 again from up here, it's going to turn positive. Subtract 1 again, it's going to turn negative, blah, blah, blah. So it is an alternating series in this case. Did I hit that thing? I did. All right. Let's see. All right, you all try this one. So binomial 1 plus x raised to the 2/3.
This only works whenever it's 1 plus x. Again, not like a 2 plus x,
There are ways.
but not
But yeah.
this method.
Yeah, there are ways you could, if you had 2 plus x, you could write it as, there are ways that you could rewrite it to try to make it fit the binomial form. You could write it as 1 plus quantity 1 plus x.
So if the computer is using the Taylor polynomial to solve these for us, what value is it comparing it to know it's accurate to the number of decimals it's showing us?
So when we looked at our, when we looked at the remainder thing, which was somewhere back
I was
here.
gone that day, that's probably why I'm confused.
Yeah, so the remainder thing back here, here is how it knows. So the way that we find the remainder is that there is this value c between x and a that we can't find. It's basically the first unused term in the Taylor polynomial. So if you're going out to the third order, the error is given by the fourth order term, and it will use this. So we can't find this c value, but what it's going to do is find a bound on that function there. So it's going to look at the next derivative's bound,
Gotcha.
and this is the number that we want less than point whatever it is. So that is the method that it'll use. Not trivial.
Thanks.
Absolutely. So here's our generic form. It's always helpful just to write it out in generic form first with your p-value up here. So remember that that's p, so that goes everywhere. And your k is just integers from 0 up. If we want to calculate 2/3 choose 2, we're going to have 2/3 and then we subtract 1. And then we're good to go. So we're going to get -1/9 for our next coefficient. Everybody follow the -1/9? Is that the? And then if we want 2/3 choose 3, all we do is, whoops, 2/3 choose, 3. We're just going to subtract one more time. So we're going to have 2/3 multiplied by -1/3 multiplied by -4/3.
How do you do that?
And that's all divisible by 3 factorial, which is 6. What was that question?
How do you know what it's doing up there?
So we're always subtracting by 1. So it's 2/3, we subtract 1, and then it's -1/3, and we subtract 1 again. So we do repeated subtraction of 1.
K minus 1 times.
K minus 1 times. Exactly. All right, so then looks like 1, 2 will cancel, so I'm seeing a 4 in the numerator.
8
And then-
3 to the 4th, 81.
And then 3 to the 4th, right, 81. Positive 81, is everyone seeing that? So then we have plus 4 over 81 times,
9.
oh, I didn't write that one in there, thank you, yeah. So we need our 1/9 written in here,
Minus a 9.
and then, oh, minus the 9th, yeah. So now it's becoming alternating, so this series was not, if you take away the first term, then it's gonna alternate. Ad infinitum.
Yeah, because once it goes below negative, or once it goes below 0.
Once it goes below 0, then it alternates.
But if it starts positive, then the first 2 terms will be the same. Will be positive.
So there it is.
Would it be incorrect to put minus ...
No,
Okay.
yeah, it doesn't matter. Yeah, if we know the next term's gonna be minus, we can put a minus. Yeah, totally fine. What is the x value in this case?
0.02.
So x is gonna be 0.02, right, because it's 1 plus x, so the x value is 1.02, the x value is 0.02. So we're gonna say that f of, no, we're not saying f. We're saying that 1.02 raised to the 2/3 power is approximately equal to 1 plus 2/3 times 0.02 minus 1/9 times 0.0, oh my gosh, 0.02 squared. Oh, thought we were gonna make it through a class without that darn thing. Why start now? Thank you. Yeah, let's close that thing. Let's. So obnoxious.
Before it gets into the classroom.
Yeah, before it comes and gets us. Before we get swallowed.
The soothing sound of the zamboom.
It's so bizarre. Alright, so 1 plus 2. There's 2/3. There we have it. Yeah, pretty good. Really good.
Good enough.
It's good enough.
All the way out 7 turns ago.
Yeah, pretty fast.
Could you like approximate pi in this?
Well, so if you wanted to, there's better ways to approximate pi. We're going to get to that actually today.
Do we have time?
All right, so page 9.
Yeah, there we go.
Let's roll.
Let's get to pi.
So we've got this. This kind of gets at what you were asking about, Lincoln. So this is not quite that, right? So that binomial expansion is for 1 plus x. So here's how we modify this. We're going to make this 1 plus the quantity 3 plus x. So then we're just doing, a replacement. So this will, so what we're going to do then is just, if we already know that expansion, all we have to do is make this 1 plus, and if we replace we're going to replace that x with x plus 3. So x plus 3 over 2 minus x plus 3 squared over 8. That's the expansion we just found a minute ago.
And then you just plug in whatever your x is.
Yeah, if we had to do an approximation, yeah.
Okay.
Okay, so now, one question. This is a natural way to do that, but is that a Maclaurin series? That is not a Maclaurin series.
That's our idea.
And there are places in this book where it says this and it gives you that answer, but if it says Maclaurin, we would need to do it differently, because that is a power series that does represent the function, but the center here is -3, not 0. So is there another way that you can think of doing this to make the center 0? We know that we need to target this. What have we done earlier this semester with those coefficients that weren't 1?
Divide by 4.
Yeah, we factor it out. So if we factor that out, we can do this. We could say, if we factor it through the root, it becomes a 2. And we now have a 1. There was no 4 there, but now there is. So now we have that. And so then we're going to get 2 multiplied by 1 plus, and this is going to be x over 4 going in there, so that's going to be x over 8, minus x over 4 is going in there, so we're going to have x squared. 4 squared is 16, that's going to be in the denominator, so that's going to be 80 plus 48, 128. And then we're going to get x cubed. So the 4 is going in there and getting cubed. 4 times 4 is 16, times 4 is 64. 64 times 16 is 4 to the 5th?
1024.
What is it?
1024.
Oh yeah, we should know that. 1024. 1024. Common number. Plus, etc., or minus, etc., whatever. That is the Maclaurin series.
And then
So-
is that what you were talking about earlier, where 2 series that equal the same equate function are the same series? They're just semi-different.
So if you have 2 series with the same center, it has to be the same series.
Oh, but these have different.
These have different centers. Yeah. So you can have 2 different series that are equal to the same function if the centers are different. But if you have 2 series, 2 Maclaurin series would have to be the same. 2 series centered at 3 would have to be the same. But they're going to look different if you have a different center.
So then these would have different approximations, right?
Let's find out. Good question. So if we look at our approximation, they didn't give us an approximation here. So yes, because the closer the center is to that point that the value you're approximating, that's going to give you a better approximation faster. So it's true that you could come far away. If you're trying to get an approximation here, you could use the center over here. It's just going to take more terms to get close to whatever the value is we're trying to approximate.
But we have a radius of 1, right? So they would never have
That's a good point.
similar values?
That's a good point. So because our interval of convergence is so narrow,
We only have
we only have a little space to work with.
-4 to -2 and from -1 to 1 are
Yeah.
the accurate.
So this one is centered at -3, so we shifted this whole thing 3 to the left, so yeah, -4 to -2. Yeah. All right, one more here, then we get to our last section. I can't believe it. Okay, so this is, again, based on that series that we already found. This one is easy to put into a Maclaurin series form because we're just going to replace x with -4x. So replace x with -4x. That's going to give us 2x right there. 2x. And then that gets replaced with -4x, so it still stays negative. And it's going to be an x squared. And that's going to be 4 squared up there, so 16 divided by 8 is 2. And then we put a 4 in there. This one is going to become negative. We're going to have an x cubed. That's going to be 4 cubed. 2 of them cancel, so we're going to get a 4 there, and then plus etc. So that is our Maclaurin series there. Now, what about, let's talk about interval of convergence. We actually should talk about it for this prior one too for a moment. Because here we replaced x with x over 4. So if we replaced x with x over 4 up here, we had -1 x over 4. So this one actually is a little wider than what the original one was. So the interval of convergence for this blue one is that. The interval of convergence for this one is just shifted, like we said, -4 to -2. If you replace that x with x plus 3 and you subtract 3 from all the sides. So that one's a little different. Now how about this one? Here we started with -1. We're replacing x with -4x. So it looks like that. Divide by -4. Switch the inequalities. So this interval gets narrower. So there our interval of convergence is just from -1/4 to 1/4. So it gets even smaller here. Still an infinite number of points, it's just narrower. All right, last section. In chapter 11. Shocking. Shocking.
How many sections in chapter 12? Like
3.
3?
And 12 is easy.
Looking forward to it.
I know. A little bit of break. A little bit of break. Okay, so this is just kind of an oh, that's interesting type of section. There's not a ton of hardcore math in this section. We're just going to look at using power series to do things that we've already done in different ways in calculus. Like you know how to evaluate this limit. You've done it a couple different ways. L'Hopital's rule is the most common way. And it's super fast with L'Hopital's rule, of course. But we can do a lot of this stuff with infinite series. So if we look here and we replace sine of x with its infinite series, and then we take that x in the denominator and we distribute it into the numerator, everything simplifies to that.
When you plug in a 0.
Plug in a 0, the tail goes away, and the only thing that's left is the 1. So you can use any place that you're doing calculus, like a limit, a derivative, an integral. You can replace a function, if you know its Taylor series, you can replace the function with its Taylor series. So that's all that's happening there. All right. So another one. Here we're doing another limit. It is, you could do L'Hopital's rule, of course, 0 over 0. But let's do it in this more clever way. So we're going to have the limit as x goes to 0, not infinity, 0. So we're going to plug in the Taylor series. It's usually best with these to use the expanded form and just go out far enough. so that you can see the pattern. Usually 3 or 4 terms is plenty. So there's our series. That's arctangent right there. And then we're going to subtract x, and we're going to divide by x cubed. Well, we treat this Taylor polynomial just like a polynomial, so this x and this x are going to cancel. And then we have to distribute this x cubed into the numerator. So it's going into all of those terms in the numerator, and we see that the first term is going to be -1/3. It has no x in it. The subsequent terms will have x's, so that'll be x squared over 5 minus x to the 4th over 7 plus etc. But all of the subsequent terms have an x, so when you plug in the 0, the whole tail vanishes. The only term that doesn't vanish is the first term. And so we're going to get the value of this limit to be equal to -1/3. Now this is one that is probably, I mean, using L'Hopital's rule on this, the derivative of arctan's not that bad, but you know, this one actually is might be faster. You know your power series for arctan.
Especially if you just think about it, you're like, okay, so those cancel out, and then you are left with
Just that one term.
the second term, or
The first term that
first term.
that matches the power of x cubed perfectly. All right, so now we have the mustache function, the bow tie function, whatever you want to call it. Usually you study this one in Calc 1. Most of the time you're more interested in taking the limit as x goes to 0 because it looks really interesting in there as it oscillates faster and faster. But we're taking the limit as x goes to infinity, not as interesting. But with this mustache function, as x goes to infinity, we can see from the graph that it looks like there's a horizontal asymptote. Looks like maybe it's at 1. Let's find out. So we can take the limit as x goes to infinity, x multiplied by sine of 1 over x. So we've got our power series for sine of x, the odd powers from e to the x with a switch. And what are we going to do? How do we get the power series for sine of 1 over x?
Just plug in x to -4.
Right? We're going to replace all the x's that we see with a 1 over x. So we have sine of 1 over x. We're just going to replace all the x's with 1 over x. So that's going to be 1 over x there. And all that this is going to do is put the x's into the denominator. And so we end up with this looking thing. Plus dot, parentheses. Then we distribute the x, and when we distribute this x, you're starting to see the pattern. We need one of the terms, there needs to be some simplification. And the other terms should all go to somewhere obvious, like 0. And does everybody see that all the terms here are all going to 0 because x is going to infinity, so those fractions are all going to 0. So this limit is 1. So the mustache function does indeed have a horizontal asymptote at 1. Okay. Limit of x minus 1 over natural log of x. Again, L'Hopital will be faster in this case, but not as clever. So this limit will equal the limit as x goes to 1 There is the power series for natural log of x. So now x minus 1 is in the numerator. There's our power series for natural log of x. And you're kind of seeing this algebraic pattern that we just are going to get some cancellation that's going to be nice. Okay, so now that x minus 1 is common, so we're going to divide top by x minus 1, divide bottom by x minus 1. So if we divide everything through by x minus 1, we've got that thing, that expansion, and this limit is as x goes to 1. So what's true about all those terms in the denominator besides the leading term?
I'll go to 0.
Yeah, they're all going to go to 0. So all these terms are going to 0. So that leaves us, once again, with a limit of 1. So over the weekend, start looking at your 10 power, 12 power series and start looking at the patterns. On Tuesday, I'll tell you the 3 that you need to know for sure for the test. But look at them, use them, try to get comfortable with them. One more example here, and then we'll get to approximations. So the limit as x goes to infinity. Okay, e to the 1 over x. We know the power series, the most important power series. This is the one. That's the one. If you only have one that you walk out of this class with, that's the one you should walk out of this class with. And notice if you take its derivative, you get itself. If you take its integral, you get itself. So e to the 1 over x is going to be 1 plus, we're going to replace all the x's with 1 over x. So we're going to end up with this expansion.
Wait, how did you get there?
So this power series is for e to the x.
Yes.
And we're going to replace the x with 1 over x. So that
okay.
x is
I
going to be,
gotcha.
you see it?
Yep.
So it just shoves all the x's into the denominator. And once again, we see that when we simplify, we are going to have some stuff happening.
With the minus 1.
Yeah, I missed something. What did I miss?
The minus 1 in the.
Oh, there's a minus 1 up in the numerator. Thank you. So this right here, there's a minus 1 in there. That.
Otherwise, you end up with x.
Otherwise, you end up with infinity. So those cancel. Then when we distribute the x, that becomes a 1. This becomes something that will go to 0. This becomes something that will go to 0. As all those will. So this limit is as x goes to infinity. So once again, every limit is 1. If you don't know what the limit is on the test, write 1.
Where did that one come from?
Dot
Where did the
1.
one come from?
Clearly, it's 1.
4 to 5 times.
4 out of 5 times.
The second.
4 out of 5 math teachers say the
On the
limit's going to be
bottom.
1.
When you're taking the limit.
X times 1 over x.
So this x is getting,
I gotcha. Yep, yep,
that's
yep.
being distributed
Yep.
to there,
Thank you.
to there, to there. All right, approximations. Fun approximations, not like crazy weird approximations.
All right, math teacher.
You right? All right, are we going to get to the pi one? We'll see. All right, so like I said, we can use the Taylor series wherever we see a function and do derivatives, integrals, and limits. So here we have an integral, and we want to approximate. Let's see. So we have that expansion. We found that one earlier today. Now we're going to replace the x with x to the 4th. So this integral becomes integral from 0 to 0.2. We're going to use this expansion where we replace x with x to the fourth.
Yep.
So we're gonna get x to the fourth divided by 2 minus x to the, oh my gosh. 8.
Oh, sorry.
Power.
I knew that was gonna happen. I knew it was gonna happen. Right, when we replace that x with x to the fourth, it's power to power. Power to power, you multiply. So tempting to just add them, right? So x to the fourth to the 3 is x to the 12. Yeah.
So the sum you add and multiply you.
Right? Big trouble. It's a good thing I have a red pen. Okay, so that's a heck of a lot easier. This you don't know how to integrate. Right? We don't have a technique to integrate that. I mean, maybe we could do some weird trig sub, but it's not an obvious technique for sure. But now we can integrate term by term. This is x to the 5 over 10. This is x to the 9 over 72. This is x to the 13 over 13 times 16. Eek. This goes 0 to 0.2. What happens when you plug in 0?
Everything.
Everything's going to go away. So we only care about the 0.2. So it's 0.2 plus 0.2 to the 5 over 10 minus 0.2 to the 9 over 72, 0.2 to the 13 divided by
208.
208, thank you, minus etc. And then this, yeah, that's it, that's it. So, what did the question ask? Oh, okay, so we want to figure out how far we have to go out to get to be less than 10 to the negative 5. 10 to the negative 4 was not interesting. What kind of series is this if you ignore just the first term?
Alternate.
This is alternating. So we just want to know the first term that's less than 10 to the negative 5. And then we'll just add up everything that's in front of it. So we come over to our calculator. We want to know the first term that's less than 10 to the negative 5. And once we know which term is less than 10 to the negative 5, let's guess this term. And that term is definitely less.
Yeah, it's 10 to the negative 9.
And so if we're not 100% sure, we could go 0.2 to the 5th if we think, well, maybe it's the term before it. But that, I get on my glasses on. That one's not right?
It's
There's,
just barely more.
yeah, it's just barely more.
Which is presumably why you changed it from.
Exactly.
10.
Exactly why I changed it.
The
So-
first term, 0.2,
Right?
approximation of 0.2.
So this term is less than, this is the first term that's less than 10 to the negative 5. So that means that we want to add up these for our approximation. So we add the terms that are in front of the first term.
0.200, well, 3 zeros, right?
So what do you get when you add those together? Oh, I think, did you add them?
I mean, it's just 0.2 plus 0.2 with 4 zeros, right? Or 5 zeros? 10 to the, 0.2 to the, 0.2 to the 5.
0.2 to the 5.
I'm crazy.
0.2 to the 5.
To the 5.
0.2 and then
I'm just
3 zeros, and then 3, 2.
Yeah, so there's our approximation.
I'm just insane.
All right, we have 1 minute. We can probably finish one problem here. We'll have to do the pi approximation on Tuesday. We'll definitely have time on Tuesday.
Yeah.
So here is integral of arctangent, which we do know how to do now that we know how to use integration by parts in a clever way. But if we wanted to, if you were a calculator, you can't do integration by parts.
Can't try.
You could try. If you're a calculator, though, you can integrate polynomials. So we're going to integrate this polynomial. we integrate this polynomial, we get that. And this is going from 0 to 0.35. And once again, we see that, okay, 0 gives us nothing. So we're in the same boat, kind of like the last one. We're going to see that we end up with an alternating series. And the alternating series is the one series that we have mastered the remainder for. So all we need to do is find the first term that's less than 10 to the negative 5. I'll I'll put the calculation there after class ends, since class just ended. Since we done. But you get the idea. We'll just plug those in, figure out which one's less than 10 to the negative 5, and add the stuff up in front of it. The fourth term is this one? Less than 10 to the negative 5, thank you. I'll confirm and then write the sum of the first three. All right, have a good weekend. I'll see you in week... This is week 12 right now?
Yeah.
I'll see you in week 13. It's the lucky week. There's a test.
So we have,
You put the hardest test on week 13.
Week 13.
How nice.
Timing is everything.
All the luck you can get.
test week 13, week 14 and 15 we're doing chapter 12?
Chapter 12, yeah.
And then week 16 is final.
Final, yep.
So that, the final is on a Thursday.
Thursday.
Yeah,
Thursday.
because school officially ends on the 6th.
Yeah, it officially ends on that Monday, so our test will be on that Thursday.
Yeah.
Yeah. I can't believe when you said the second, I hesitated because that seems so damn early,
Yeah,
right?
it is.
It is. Yeah. Very early.
Because we have a Tuesday, Thursday.
Yeah, it just feels earlier than usual, though. What was that, Robert?
Except for that last one, it has to be